Hi, this presentation is about a very peculiar high-redshift object that we have been internally calling the Kraken because one of our team members saw an octopus in one of the images of this object. And the monster in question is a pair of star-forming galaxies inside a Lyman Alpha halo that becomes very bright and stretched because of the effect of strong gravitational lensing. In this talk, I will explain how we combine this effect together with high-quality MUSE observations to probe the gas, the Lyman Alpha emitting gas in this system down to kiloparsec scales. But first, let me remind you that galaxies are surrounded by a gas that extends all the way out to the viral radius of the galaxy. And this is what we call the circumgalactic medium, or CGM. And it's a multi-phase gas. It has a hot phase of very low density gas, and also a cool neutral phase of gas at higher densities, and this gas is the gas that falls into the galaxy during the accretion, or the cosmological accretion, and also can go out from the star-forming galaxy by the means of outflows or AGN-driven winds. Because of this, the cool gas, the cool phase of the CGM, is very important for galaxy evolution. But how can we detect and measure the properties of this gas? One way is to observe the 21 centimeter line emission with the canonical neutral gas tracer, but this can only be done up to very low redshift because it's an intrinsically very faint line. Another popular alternative is to perform absorption studies, tracing the metal low ionization lines and also hydrogen lines in absorption against a background quasar, for example. But this has some drawbacks. For example, you can only probe one line of sight at a time, of course with a few exceptions. But if you want to probe the circumgalactic gas in emission rather than absorption, your best chance at doing so is by targeting the Lyman Alpha line. This is because photoionization models tell us that in a wide variety of situations and physical parameters, the Lyman Alpha line is the brightest by far in the interstellar medium of galaxies, and also it can interact with the CGM. And for this reason, the Lyman Alpha line is like a two-sided sword, because it's very bright, and it can, because of its interaction with the CGM, we can probe the properties of the CGM, but also the interactions lead to very complex radiative transfer effects that complicate its interpretation. But anyway, this interaction can take many forms. This is because Lyman Alpha is a resonant line, it's a resonant transition. This means that for a nitrogen atom, it's very easy to emit and reabsorb and then re-emit a photon at this wavelength. And this causes a photon originated in the star-forming regions of the central galaxy can bounce in the neutral gas clouds in the CGM and scatter off the system at very large distances. You can also produce Lyman Alpha by photoexcitation of the gas by a very strong radiation field. And for the gas clouds that are falling into the central part of the halo, you also expect them to glow in Lyman Alpha by a process called gravitational cooling. And finally, you also have the contribution from dwarf satellites residing in the halo. So these are probably all reasons contributing to the emergence of extended Lyman Alpha emission around galaxies. This was discovered in the era of narrowband surveys, but now with state-of-the-art IFU instruments, we can very easily, or at least more easily than before, detect them around individual galaxies. And here on the left, I show you a stacked image of a very big chunk of the sky that shows Lyman Alpha in almost every direction. And this was a result by Wysotsky 4 years ago. To the right, I show a variety of simulated Lyman Alpha halos and they come to show that they come in a wide variety of sizes, from very small halos to very large halos associated with overdensities on protocluster environments. Also, the same simulations show very complex substructure in these objects, and also clumpiness and things that with our current instrumentation we cannot very easily detect. But one option to detect and study these variations and these properties is to observe and target strong lensing clusters. And the first one to perform this idea, the pioneer of this idea, was Swinbank in 2007, who observed the first lens Lyman Alpha halo. And since then, and with the appearance of MUSE, this has become a very efficient way to produce special properties of Lyman Alpha halos. And these studies have shown that these halos do in fact show variations in the line shape, special variations in the shape of the line, and also offsets between the Lyman Alpha emission and the underlying UV continuum. In this presentation, I will talk about this particular system that is formally called J1226, SCAS J1226, and it was discovered almost 12 years ago by using the Lyman break technique on Sloan digital sky survey data, Sloan data, and we now have HST imaging for this field, which revealed the very clumpy morphology of the galaxies, and also there is a very detailed lens model based on this HST image that allows us to know the intrinsic properties of the galaxies. And we know now that these are two galaxies. This one is lensed many times. It has one half here, and then a counter image here. And this other galaxy, this other arc is another galaxy. Together, they don't add up more than 10 to the 10 solar masses in stellar mass. And also, the star formation rate is very moderate at 25 stellar masses per year. And also, Galaxy B, it's a bit different to Galaxy A in the sense that it has a shallower UV continuum slope, and also detection of far infrared continuum, which indicates that it could be more dusty than the other. Taking the best lens model we have, we can reconstruct the emission in the source plane, and we see that these two galaxies lie very close together at less than 15 kiloparsec in projection, and also that looking at the nebular emission lines of these two galaxies, we see that their systemic velocity is very similar. All of this suggests that they are interacting. They are a pair of galaxies that are in a merging or a close flyby state. So what's new? What's new about this system is that we have MUSE data taken by the gravitational tomography collaboration, and yes, these are 5 hours of the wide field mode MUSE observations with adaptive optics, and collapsing the data cube at the Lyman alpha wavelength, we observe something like this: a very bright and very extended Lyman alpha morphology with several clumps and features. So in the rest of the presentation, I will show our analysis of this source in both the spatial and spectral dimensions. So especially these Galaxy A and Galaxy B show very similar profiles. They have an exponential core that follows very closely the UV morphology of the galaxy, but then there's a second component of extended emission in Lyman alpha. Spectrally, the line is asymmetric, with a wing to the red wavelength, and if we take apertures centered on the galaxies, and then an aperture taking only the spaxels of diffuse emission, this is without any continuum, we observe that on top of the galaxies, the Lyman alpha emission is narrower and less redshifted than in the diffuse halo, which is shown here in the blue line. The blue line is broader than the other two. To look at this in more detail, we performed a special binning of the emission using the method by KINEMATICS et al. 2019. And this means separating the source plane in regions with more or less equal flux, and then extracting the line profile in them, and then characterizing them using a fit of a symmetric Gaussian model, just to parameterize the width of the line and also the velocity of the peak. And we were able to produce these maps. This to the left is the surface brightness map with the UV continuum contours on top, and also the location of the dust detection. And here we have the map of the width of the line, and we see the same that we saw in the integrated global apertures. That is that the beams that are closer to the galaxies have smaller widths than the outskirts. And something similar for the separation between the peak and the systemic velocity. So at the outskirts we see a redder velocity. And these are very similar because there is in fact a correlation between the width of the line and the shift between the systemic and the peak of the line. And we recovered this for individual parts of a single halo, but this was already found for different halos in a per halo basis, meaning a sample of Lyman alpha emitters. The Bergham et al. 2018 measured this correlation, and it was again in resolved studies also found by Claessens and Leclerc. As well, we find a dependence of the peak shift with the surface brightness of the beam. So the brightest beams show less Lyman alpha peak shift separation. But in any case, these quantities, like the Lyman alpha peak shift and the width, cannot be directly related to any physical quantity because of the radiative transfer effect. So to go one step further, we wanted to model the lines with physical models, and these are radiative transfer models using the Flareon code, which implements the typical spherical geometry, expanding geometry, and it has two flavors. It has a galactic wind, where there's a central source of Lyman alpha photons and declining the density profile of gas, and a thin shell model, which is essentially the same, but now the gas is distributed around a thin shell of gas. And knowing fitting the grid of spectra produced by these models, we can infer properties like the expansion velocity, also the column density. We can separate the velocity from the density, and there's also a parameter that's the optical depth. And in our case, we also left free the systemic redshift, although we knew the systemic redshift for the galaxies. We wanted to see how well this approach recovered the true systemic redshift in the beams with continuum. And these are our results. This is the map of the expansion velocity, and we see that the expansion velocity go as high as 350 kilometers per second with some gradients, although the distribution of these gradients is not the same. It depends on the model, and the same goes for the column density of neutral hydrogen, which doesn't show very strong similarities between the two models. And finally, for the systemic redshift, we do not recover the true systemic redshift as measured by the nebular lines, but we do recover the fact that this galaxy is more redshifted than this one. With this in mind, we ask ourselves which scenario is the most consistent with our observed kinematics. We have three options here. We can have inflows and infalls as dominating kinematics. We can have outflows, or we can have merging activities. The first option is, of course, ruled out because we don't see a blue peak in the Lyman alpha line, and we also don't see any redshifted ISM absorption that will be expected in this scenario. For the outflows, we do see a dominant red peak, and we see also blue shifted ISM absorption, as shown here by these low ionization metal lines in the UV spectrum of the galaxies that are redshifted with blue shifted with respect of the systemic velocity, and also have a blue tail. They are asymmetric, and the velocities are very consistent with what the radiative transfer models show for the Lyman alpha line. So this is their deepest point is about a velocity of 300 kilometers per second. As for the merging, we cannot really say anything much yet because we do not know the internal kinematics of the galaxies. Finally, we report the discovery of a candidate satellite galaxy. So we were looking at the one of the local peaks of Lyman alpha emission, and we found that the lens model did not predict any multiple image from the two galaxies here. So we confirmed this detection, looking for a continuum counterpart in the UV data, and modeling the galaxies of the cluster. We removed them, and in the residual we found this excess of emission. So we attribute this as a counterpart to this local peak of Lyman alpha in the halo. And we believe it's a very low mass Lyman alpha emitter with this property, with a very high equivalent width, very low luminosity, and it contributes about 2% of the total Lyman alpha luminosity in the source plane. So as a summary, we have studied a pair of star-forming galaxies inside the Lyman alpha halo. In agreement with previous studies, we found that the line is redder and broader toward the outskirts of the galaxy. We also found that the global signature of the system is that of an outflow, but there are variations across the halo. That the modeling allows velocities up to 350 kilometers per second for the outflow. And we also have a confirmation of a satellite galaxy in the halo contributing 2% of the total luminosity. To assess what is the role of the interaction between these two galaxies, we are pushing an ALMA program that was approved in the cycle 8 for obtaining C+ observations of this system. So in this way, constrain the internal kinematics of the two galaxies and see what is the true picture of the kinematics and whether the halo gas is coupled with the ISM kinematics. We also want to know what is the escape fraction of Lyman alpha, so we have to compare with H alpha, and also what is the rate between radiation coming from fluorescence and the radiation coming from just scattering. Also, we are not really sure of the sources of ionization. We believe it's just star formation, but we don't really have any indicator that rules out an AGN. So for this will be very important the upcoming JWST program template, an early release science program led by Jen Rigby, that will get IFU spectra of galaxy A. So we will have resolved nebular spectrum of this galaxy. So we will be able to compare H alpha size with the Lyman alpha size, and also we will be able to constrain the presence of any AGN by the luminosity in the MIRI bands. So this was it. I hope you enjoyed the presentations. Goodbye.